Hey students, so this is the second video. In this one we're going to do a problem where we have two different water samples at different masses and different temperatures, and we're going to mix them and we're going to figure out what the final temperature is and calculate that. And then also we're going to do a basic calorimetry example here where we have a particular substance, certain amount of it, and we will use a calorimeter and a certain amount of water and temperature change to figure out how much heat of combustion and molar heat of combustion is for the substance. All right, so the first one is this example where we did this in our homework assignment a little while back. We had two different samples of water with different masses and different temperatures to start out with, and then we mixed them together. So when we do this type of problem, we assume that all of the energy that is released by the warmer substance is going to be absorbed by the cooler substance. So one way that we write that is that the negative mc delta T is equal to the positive mc delta T. We're not going to get into this video where we figure out how that was created as an equal equation. So if you'd like to know a little bit more, just ask your teachers, ask me or ask Mr. P. But this particular part right here is the variables for the released heat, and then this is for the amount absorbed. So how do we figure out what is releasing, what's absorbing? Well, basically, if we look at our problem and we see that something is colder, something is colder and something is warmer, we know that the colder thing is going to get warmer, so it's going to have to absorb heat. So that's going to be in, all these numbers are going to be for the colder temperature substance, and then all of these are going to be for the warmer. That's releasing heat, getting colder. All right, so let's fill this in. So releasing heat, that would be, so it would be negative 32.2 grams of water that is at 46.8 degrees Celsius. And this is well within the range of liquid water, so that's 4.18 as a specific heat. And what we don't know is the final temperature. This is what we're trying to figure out. So we're going to leave final temperature as a variable. I'm going to call it TF. And we're going to subtract, and we're going to say that the initial temperature for the thing releasing heat is 46.8. We're going to set that equal to the other substance, which is 32.2 grams. The specific heat, oh my goodness. Specific heat is 4.18, because again it's at 14.9 degrees Celsius. Again, we don't know the final temperature, so we're going to leave that as a variable, and we're going to subtract 14.9 degrees. Okay, so the final temperature for both of these is going to be the same temperature. They're mixing together, and so when we mix them together, they should finally reach a point where the final temperature is the same for both substances. So we can say that that is a variable that's equal to each other. The final temperature on the left, the final temperature on the right, the same thing. So we can actually solve for final temperature. So to do so, we are going to take the value of the mass, and we're going to multiply 32.2 times 4.18. We're going to get 134.6. Negative 134.6, and this is times TF minus 46.8. Oh my goodness. and this is equal to, and then again it's 32.2 times 4.18, so it's 134.6 times TF minus 14.9. Okay. To make this simpler, we're going to take this. I'm just going to put a little bit more room. Okay, so what I see here is that it doesn't always work out this way, but in this case, we have the same mass for both of the samples. And so that makes it easy for us to cancel out the numbers in front. So negative 134.6 divided by, and then negative 134.6. And then we get temperature final minus 46.8 equals negative, and then, oh my goodness, temperature final minus 14.9. Okay, so what we can do is we can add the 46.8 to both sides, and what we're going to get is temperature final, my goodness, temperature final is equal to, and then this would be, so temperature final, and then this is negative, and then this is negative negative, so that's positive 14.9 plus 46.8, so that's going to be 61.7. Okay, and last but not least, we're going to take this over here and make this 2 temperature final. We're almost there. 2 TF is equal to 61.7, and then temperature final, when we divide by 2 on both sides, is roughly equal to 30, let's see, 30.85. Oops. All right, and that's degrees Celsius. Okay, so that's the final temperature for the substances. Moving on to calorimetry. So this is the second part of our quiz, and this is only for Mr. Halpern. For Mr. P, you just have heating curves, but we went a little bit further in my class, so we're going to have this. So when you solve these types of problems, we're going to assume that the amount of heat that was in a calorimeter, which is this basic setup where you have a substance that is burning, and you have a can with a certain amount of water that's being suspended over that. We assume is that the amount of energy that is absorbed by this can, absorbed, is equal to the amount of energy that was released by the fuel source. In class, we used a candle and just a can of water. Okay, so we're going to have this basic setup here. Now, the one thing we don't know is how much, like we don't know the numbers Q equals MC delta T for the amount released, because we might not even know what substance we're talking about, so we don't know what the specific heat capacity is for that. We might not know the temperature change for that, but what we can figure out is the amount of energy absorbed by the water, because water is a really easy thing to measure the temperature change, and we know the specific heat of water, and we can figure out the mass of the water. So we can figure out that and then say that they're both equal. So we're going to solve for this problem. So we're going to read through this. If 200 grams of hexane, C6H14, is combusted in a bomb calorimeter, which is a higher, like industrial grade calorimeter that's a bit more concealed than what we have in our class. It contains 5,650 grams of water. Calculate the heat of combustion and the molar heat of combustion of hexane if the water temperature rises from 0 to 55.4 degrees Celsius. Okay, so we're going to plug in our numbers for water and set that equal to how much energy was released by the hexane. So we're going to say that Q is equal to mc delta T, so mc delta T is equal to the amount of heat released, and then we're going to plug this in. So the mass is 5,650 grams. The specific heat of liquid water is 4.18, and the temperature change is so final minus initial, so 55.4 minus 0. Okay, and this equals so 1,308,381.8. So in kilojoules, we're going to write this out because this is a big number. So in kilojoules, we're going to move the decimal place over 3 times. So actually, this is equal to 1,308.4 kilojoules. Okay, that's how many kilojoules were released by the fuel, the hexane, right? And that's by calculating the amount of energy absorbed by the water. So we can say those are equal to each other. Is it a perfect assumption? No, it's not a perfect assumption. There's some heat that's released to the environment, to the canister, to the calorimeter itself. So it's not a perfect amount. Inevitably, the amount that's calculated here is probably going to be less than what actually was released by the fuel. So how do we figure out kilojoules per gram? What we do is you take the amount of kilojoules that we just calculated, and we're going to divide by the amount of grams that was burned. So we found out by rereading this that we have 200 grams of hexane that was combusted. So we're going to divide by 200 grams. And we're going to get the answer. So our answer would be divide by 1,000, which is what we did for getting kilojoules, and divide by 200, and we get 6.54. So it's 6.54 kilojoules per gram. Okay, so that is the heat of combustion. Now, the molar heat of combustion is simply taking the molar mass, which is, in this case, so for hexane, it's C6H14. So C6H14, the molar mass would be carbon, which is 12 times 6, plus hydrogen, which is 1 times 14, equals, so that's 72 plus 14, 86 grams per mole. What we do is we take this number, 86 grams per mole, and we multiply it by 6.54 kilojoules per gram. What you notice here is that we have grams on top and grams on the bottom. What we're going to get is a final answer. We multiply these two, 86 times this, 6.54. We're going to get 562.6. And that's kilojoules per mole. That's the molar mass, or molar heat of combustion. Okay, that's it.